Sorry, we're having an issue with the link where our speaker hasn't been able to get in and one of the other facilitators hasn't gotten in yet. So we're trying to sort that out. In the meantime, Matt, you want to say anything about the field trip?
Yeah, I can. Hi, it's Matt Gregory. We'll be meeting and going on. Everybody should have gotten the location. I believe it's called Pruitt Park. So it's on the north side of Spring Creek, relatively close to I-45, and we've got a plan to meet there and go on a brief kind of little hike, I would say. And don't think it's it's not much of a hike. It's probably, I don't know, kind of a quarter of a mile, if that, to the creek, and then back. So there'll be a little bit of not really much relief. It can kind of get steep near the banks and a little bit slick. We're not going down to the creek, obviously. We'll just go to a sandy bar there called a point bar, and then have a discussion kind of around geology and stuff in the area. There should be ample parking near there.
And Matt,
yeah,
it's Tom Philpott. It's technically Montgomery County Preserve. It's off of Pruitt Road, but
right.
It's the beginning or end of Spring Creek Nature Trail, essentially. So
right. Yeah, because it's kind of and it's we'll kind of, well, you know a ton about these trails, Tom. So I know you're in the BLC crew and all of that. So there's like two options we have. One is it's an oil service road back in there. So we'll kind of have to be mindful of that. I've only seen kind of tanker trucks here and there and pickups, and they tend to be fairly careful.
There won't be any issue with that on the weekend. And they used to have that road blocked off all the time. But I think we finally figured out an agreement to let us across that bridge, basically. And
right.
we've never had a problem with any vehicles in there. So
yeah, because I was there probably a couple of weeks ago, and that bridge was open.
Yeah, I was there on Thursday and it was open.
Yeah. So we've got a couple of options to kind of get down closer to the creek, and we'll kind of gauge like how muddy and everything it looks over there, because we don't want to put anybody in a tricky situation related to slick slopes and all of that kind of stuff.
Yeah, when I was there on Thursday, there were some mosquitoes, but I don't think we're going to have that problem today.
Yeah, it's a little breezy and cooler.
Virginia, this is Lisa. Our speaker is on now.
Yes. Yeah, the only other thing I would add is when I went the other day, I took a walking stick with me, which kind of helped getting down the banks if you're worried about that sort of stuff. I'll bring a couple extra ones, but if you have one and you're worried about it, you might bring your own.
Yeah, and bring just some water. It's not hot, but it's always good to have a water bottle with you. And go at the pace you're comfortable with. There's nothing we have to do, so we'll keep safety in the forefront.
Well, we have geologist Bill Foss, who's going to talk to us a little bit about geology. If you want to share your screen and introduce yourself, let me find you on my screen.
Can you hear me?
I can hear you. There you are.
Okay, great.
I will spotlight you, and then if you want to share your screen, that would be awesome. And introduce yourself.
Yep. Hold on just a moment. Okay.
Perfect.
Okay. So yes, as she said, I'm Bill Foss. I'm a geologist. I grew up as the son of a geologist who was originally came out and was involved in training the Apollo astronauts in geology, and then went on to become a mining geologist. So every year from about the time I was born to about the time I was 12, we spent visiting my dad at summer mining sites where he was doing exploration programs. So I think I was about 12 before I realized that not everybody was learning geology on their summer vacations. But I picked up a lot of rocks, handed them to my dad, asked him what they were, and found out that I was a master at finding leaverites, as lever right there. So I was not a great geologist as a kid, but I decided to follow in his footsteps, and now I actually do environmental geology. I work for a company that works mostly on Department of Defense sites, cleaning up Air Force bases, Army bases, things like that, ammunition plants, stuff like that. Basically cleaning up all the messes that the government has made over the last 50 to 70 years since about World War II. And I'm going to talk to you about the geology and soils of Texas, and I added with bonus case studies on here because this is the first time I've given this talk. It's a 2-hour program instead of an hour and 15 minutes. So you guys get the part that I always end up rushed at the end trying to talk about, how does geology affect us? How do we affect the geology around us? And this time I get to add a couple extra case studies, talk a little bit more about some things that are going on around us where maybe we're trying to work with or against the local geology and geomorphology. So hopefully y'all enjoy that part. I always get the best comments about all, talking about how it affects us. So hopefully we'll get a chance to do more of that this time. So just to go into a little intro, when I was involved in making the geology curriculum for this, and I think the geology curriculum was originally heavily focused on stuff that if you really already knew geology, it made a lot of sense to you, but it wasn't great at kind of teaching you the basics of geology. So we wrote a little more into that, and I think it's a pretty good curriculum, but I still think the soil curriculum is a little better than geology curriculum. And since I'm a geologist and not a soil scientist, I'm going to weigh heavily on the geology side, but just wanted to kind of walk through the goals and kind of tell you what to expect. The unit goals are to become aware of and understand kind of the processes and the interactions that were instrumental in forming the geology of Texas. I'll go through a series of maybe 8 to 10 slides that'll kind of show us kind of where Texas has been through time and what the geology formed during those times was. We'll talk about the geologic history of Texas a little bit. I'm not going to go through and describe every landform and talk about the geology, but I'm going to kind of show you how the geology influences the ecoregions and the soil formations and things like that. And we'll talk about how the landscape around the Houston area and generally the southeast and upper coast of Texas formed and what it means for us today. And then we'll talk a little bit about the hydrogeologic cycle. Not going to go into all possible sources of water. I think would be a great topic for another talk. And if you ever wanted to hear all about the water planning process, my wife works for the Water Development Board and would be glad to talk to you guys. But I'll talk a little bit about how it's all related, how we influence geology and groundwater and other sources of water. But I'm not going to get real deep into that today. And then on the soil side, they want to talk about describing the chemical and physical properties of soil. My goal for this is for you to understand the difference between geology and soil and how to find out a little more information about both. Mainly in the sense that a geologist is looking at a lot more than a soil scientist. Soil scientist is looking at the upper 60 inches of the soil profile, and that's what they're describing and discussing. And a geologist maybe their maps and their reports may not even talk about the top several feet or the top 100 feet of depending on what the report is about. So just understand your source and understand the difference between a geology map and a soil map and what the two of them mean. I'll talk a little bit about that. So I'm assuming everybody has had at least some exposure to geology or earth science or something like that. Maybe it was a college class, maybe it was a high school earth science class. But I'm just going to kind of review a little bit about kind of the big picture, the big and the little pictures of how landforms happen and what influence geology has on the different parts of the ecology around you. So the definition of geology is a scientific study of the origin, history, and structure of the earth. when it comes to that, there's the big picture, which is we have a three-part Earth, if you will. We have a solid core with a metal center that may have a liquid metal area around it. Then we have the mantle, which is a kind of a partially melted, very, I don't want to say soupy, but very soft layer between the core and the crust. And then the crust is just this outer skin of rock. And if you want to think about it in scope of size, think about a bowl of chili con queso at the Mexican restaurant. When it starts to cool off and you get that slight little skin of cheese across the top, that's what the crust of the earth is in the context of the bigger picture. We're living on a very, and we've explored a very tiny amount of the Earth's overall structure and crust. So pretty much everything we know below the crust is from geophysical sensors, from looking at magma that has erupted from the mantle in places like ocean ridges and things like that. So physically, we know very little about it. Theoretically, we know an awful lot. And so when people talk about the mantle, people talk about the core and the different structures involved, just understand that it's all very theoretical, and it's what we see and what we know is from sensors, not necessarily from direct physical contact or direct physical experience. So plate tectonics, you can have multiple college level courses on this. I'm going to give you about three or four slides, I think. So understand that everything that I'm saying is a somewhat of a generality, but it gives you the big picture. But for the geologists out there listening, you may say, oh, you know, that's not exactly right. You're absolutely right. There's places and things where there will be exceptions to this, but I'm really talking in generalities, the general case. And every rule in geology has an exception, so just understand that. So when we talk about plates, like I just talked about that thin skin, the plates are solid layers that are riding around on top of the semi-molten mantle. So as heat comes from the center of the earth and rises to the surface in the form of eruptions of magma from the mantle, it's pushing these plates back and forth, and that's the energy for plate tectonics. So as I just said, yeah, as that upwelling of magma comes from the mantle due to the heat, it fractures the plates, moves them around, creates new crust, kind of dissolves new crust where the plates are kind of pushed together and crushed under each other. Subducted is the term you'll hear. And so when we look at new crust forming, it's generally at mid-ocean ridges. And I'll show you a graphic of that here in just a moment. But if you think about oceanic plates as new crust that is relatively dense and usually cools underwater or very near the surface. And so it cools very rapidly, forms a very dense material. And it's generally in rifts like we have, you know, Iceland is the north end of the mid-Atlantic rift. There's a Pacific rise and other structures all around the planet. And I'll show you a map here in a minute. But that is the engine that pushes the plates, is the eruption of new mantle at these rifts. And then continental plates are older, and I say lighter, but less dense is the better term. Material that is created by collisions, by eruptions within the land surface, by uplift from the intrusion of magma. All these different processes create continental plates that are thicker. An oceanic plate may be, 10 kilometers, 20 kilometers thick. Continental plate may be, 50, 100 kilometers thick. So they're much thicker plates, much more material, but not necessarily as dense, maybe lighter material relative to what's in the oceanic plates. And they're usually much older, but they've been through a whole series of collisions and processes that have added material over time to the top of the plate. So this is a graphic, and I don't know, can you guys see my cursor at all? I forgot to go in and enlarge my cursor.
Yes, we can. It's small, but we can see it.
Okay, good. So if you guys have any trouble seeing anything or have questions, please let me know. But I should have said that earlier. But as I said before, you've got this inner core, which is solid, mostly nickel, iron, other heavy metals. The outer core is a liquid core, but it's liquid in the sense that it's under great pressure, under great temperature, but it's liquid at that state. And then between the core and the earth is this large area of mantle. And if you think about it as just very gooey, viscous material. But what happens is there's heat generated by radioactivity in the core that is trying to rise to the surface. So radioactive decay creates the heat. The heat is trying to rise to the surface and get out, if you will. And so what happens is this mantle material rises and transports that heat with it. So if you think about it as just a giant heat engine, that's really where this what drives plate tectonics. And so you have a ridge here in the middle. Assume these are two oceanic plates and they're being pushed apart, and eventually they reach another plate that's being pushed from the other direction, and we have a collision where one plate, if they're both oceanic, may wind up going under the other, or if this is a continental and an oceanic plate, the oceanic will go underneath the continental plate. And that's where we have the ring of fire, where you have the big earthquakes around the world, the Andes, the Cascades, and up around Alaska and over into the Pacific. Some of the largest earthquakes we get are because this is not a smooth process. As that plate is moving underneath it, it gets hung up at times, and eventually when it gets enough pressure on it, it pops one of these faults that's in this overlying layer here, and that essentially this tongue of the other plate gets stuck, pulled down, and then snaps back. And I remember in the Christmas Day or the tsunami that they had a few years back, they said the plate motion or the fault motion along part of that was something along the lines of 100 feet of fault throw in that one earthquake that caused the giant tsunami. And so these can be some dramatic motions, but most of the time it's a small accumulation of strain over time. You may get small earthquakes, you may get small faulting episodes, but the end result is you generate a lot of energy at these collisions, and that is reflected in the seismicity and the amount of earthquakes that happen there. So we talk about tectonic boundaries, and just to understand why I'm going here with this is that these tectonic boundaries, the collisions, the energy that's generated by these tectonic movements and by the topography that's created by them is the driver of all of the other geologic processes we're going to talk about. Topographic relief is created by tectonics, and that topographic relief is what drives all the sedimentary processes, all the alluvial movement, it can control weather in an area, and we'll talk all about that. But just understand that this engine of plate tectonics is what creates all the conditions necessary for all the other processes of geology and geomorphology to take place. And I really feel like you guys are missing out because I talk with my hands and I wave a lot. So I feel like you guys are getting half the business here. But if you see my hands waving around, it just means I'm exercising my inner Italian. So tectonic boundaries, we have divergent boundaries. I just talked about that a little bit, where we have a rift where magma is rising from the mantle, the crust separates and moves in opposite directions away from each other. And then we have convergent boundaries. Subduction is labeled here, where you have two plates moving towards each other, and one plate is denser or thinner and ends up being pushed underneath the other plate. That's what's called a subduction zone, where those two plates are colliding and one is being pushed under the other. And then we have transform boundaries, where one plate is moving past another laterally. So you have a boundary between two plates. They're not necessarily colliding or moving apart, but they're sliding past each other, and we can get a great deal of seismicity and energy formed in those areas as well. And the one I didn't mention under convergent boundaries is if you have two continental plates collide with one another, they're not necessarily going to dive one under the other. Sometimes they just make a gigantic mashup of everything that was that continent, and it all gets pushed upward. And I'll show you some examples of that as well. So this is a generic graphic that shows kind of these different boundaries to some degree. And I can kind of give you an idea of where you might see these on the planet. So this first one in the middle here is an ocean ridge that's spreading. You've got mantle coming up, you're pushing on a plate, you're pushing on a plate, they're going in opposite directions. And sometimes along those boundaries, you have points where they're spreading at different rates. It's not all a uniform process. And so where one side is moving differently than the other, you get kind of kinks in these ridges where you have a line of the rift here and a line of the rift here. They're both spreading, but they're spreading at different rates. And so right here in the middle between them, you get a transform boundary where you have this plate is moving this way. This plate up here is moving to the other direction, to the right. And so in between those two sections of rift, you have a transform boundary. A good example of that is the San Andreas Fault. You've got spreading centers to the south down into the Gulf of California down there. And then to the north up along the Cascades and offshore from the Cascades, you've got spreading centers. And in between the two, you have a transform boundary that runs down through San Francisco and Los Angeles and down out to the sea there. And so everybody talks about, you know, California may fall into the ocean one day. It's not really that going to work that way, but it may be that at some point long time in the geologic future, Los Angeles will be a suburb of San Francisco or vice versa. So the different sides of that fault are moving north and south, not east and west. And so the faulting that they get and the earthquakes they get are related to that transform boundary. Out here is an example of a hot spot over on an oceanic plate. Think of the island of Hawaii. And this plate is moving over that hot spot in the mantle. And so when you look at the Hawaiian Islands, there's a chain there that tells you what direction the plate is moving. The plate is moving to the northwest in the vicinity of the Hawaiian Islands. And so as it moves over time across that hotspot, you get a series of volcanoes formed where that magma has reached the surface and created an island. And even as we speak, the island of Hawaii, most of the volcanism is happening at the far southeastern edge there, Kilauea, and then offshore there's another volcano forming out there that's also eventually going to either form another portion of the big island, or it'll make an island of its own as it becomes more dominant in the volcanism there. But the farther north and west you go in the Hawaiian Islands, the more the magma has cooled, the more the volcanism has died down. There still may be volcanism that'll happen on Mauna Loa or some of the other volcanoes on the Big Island from time to time, but the dominant volcanism right now is happening at Kilauea. And when you get up to Kauai and some of those islands at the northwest edge, they're much more lush, they're much more green, mainly because there's been more time for that lava that was erupted in the past to have broken down and become fertile soil and develop more. So it's interesting to see the chain of ecological development as you go from northwest to southeast, because it's a function not only of kind of different weather for the sizes of the islands, but it's also a function of the stage of degradation of the magma, or of the lava, I'm sorry, that has been erupted there, breaking down and becoming soil. So the more it breaks down, the more rich the soil becomes, and the better it becomes as an ecological site for vegetative growth. Over here to the left-hand side of the drawing, we've got what I was talking about with a subduction boundary, where you have one plate going under the other. If you think about the area over by Indonesia and kind of the South Pacific and the Eastern, or sorry, the Western Pacific, you get island arcs forming where this dense crust and all this accumulated detritus on top of it is getting subducted underneath another plate. And as it does that, the temperature and pressure profile changes. And so what was stable here at the surface when it was deposited is now unstable down here, melts down to a liquid or into gases and starts moving upward. And you get a chain of arc of islands here, a volcanic arc that is formed as a function of the melting of that plate as it gets moved down. And some of that material is light and wants to go to the surface, and so it will go up and form volcanoes there. So Krakatoa, all these, kind of famous Pacific Island arcs. Also, the Aleutians up in Alaska is a good example of this. That entire island chain of the Aleutians is volcanoes formed from subduction. The Good Friday earthquake was a subduction zone earthquake up in Alaska. I think it was 9.3 or something like that. So, again, intense forces acting at these locations and intense earthquakes and tsunami generation, but also heat and energy from magma eruption along these arcs. And you can also have a continental arc in the same way, where you have, if you move over to the right hand side here, where you have an oceanic plate going underneath a continental plate, you get something like the Sierra Nevadas and the Cascades, where these are all volcanic peaks with differing ages and differing levels of activity. But funny story, in the past, when my dad was working with the astronauts up in the Pacific Northwest, they went to a series of the volcanic sites up in the Cascades, and they had a press conference later. The local news people wanted to talk to him and ask what they were doing, and so he said, "Well, I'm teaching the astronauts about volcanic geology using some of the dormant volcanoes around here." And they said, "Well, you mean extinct, right?" He said, "No, they're dormant. They could still erupt." And I said, "So you're saying Mount Hood could erupt?" And he says, "Well, yeah, it's possible. It's still an active volcano, but it's dormant. You'd get a lot of warning before it happened." But he said, "But it could erupt tomorrow." "Well, not, it's really unlikely, but it could." Well, yeah, I mean, it's still active, so it could erupt at any time. And so the newspaper headline the next day was, "NASA scientist predicts Mount Hood to erupt," and they had asked him what would happen if that happened, and he said, "Well, Portland would be buried in ash." And so NASA scientist predicts Mount Hood to erupt, Portland to be buried in ash. And so Deke Slate came and had a stern word with my father about stick to the training, don't talk about the what could happen. But he was vindicated a bit later. It wasn't Mount Hood, it was Mount St. Helens, but Portland got a good coating of ash from an active volcano. So these are still active to some degree, even down at the southern end, Mono Inyo crater and some of those things down in the California range are still active volcanoes and still active hotspots where you could see eruptions in the future. And then the other thing we get is you can get rifting within continental crust as well. The basin and range is an area that is kind of it's not really a rift yet, but it has a lot of spreading and growth going on that could be that in the future. But a good example of this now is to look over in the east end of Africa. So the East African Rift is an area where there is rifting going on, pushing parts of the continent apart, and eventually that rift in the valley created will reach the coast, and you'll get a sense of an inland ocean starting to form if that rift continues to spread. And there's no reason to believe it won't, for at least for the near future. So we've talked a bit about the big processes. Any questions on that? I haven't looked at the chat to see if anybody has any specific questions, but if so, please speak up and let me know. So we talk about the big picture. Now let's talk about the small picture. So as I mentioned, tectonic forces create topographic relief. They create, elevation to our landform. And it's that elevation that interacts with the atmosphere. It interacts with, running water, falling water, and freezing and thawing and things like that. And that is what allows all of the other landform level geomorphology that we see to happen. Water is by far the most significant erosional agent on the planet. Even in the middle of the desert, the winds will move sand around, make some dunes, things like that. But when you get one rainfall, you can completely transform the landscape. And if you've ever seen a flash flood out in Arizona or New Mexico or those areas, when you see one of those coming down a channel, there's giant boulders often rolling in the middle of that channel. The power of the water and the power of flowing water, particularly in an area that doesn't see it all the time, creates significant erosion, moves significant quantities of material around. And living in the Houston area along the upper Texas coast, that alluvial action of water transporting sediment is what has created everything around us. We don't see big mountainsides. We don't see the bedrock. What we see is the result of all that erosion and the result of the deposition of that sediment as the water reaches the coast. And that's what's formed all the landforms around us. The next thing that also happens that water kind of facilitates is chemical weathering. So when you get acidic rain, when you get acid from organic degradation and that sort of thing, you can weather rock and transform it into soil by breaking down the strength of the rock, breaking down the bonds and breaking down some of the minerals that hold the rock together. And various rocks are more or less resistant to weathering like that. So that's how we kind of get, uneven landforms where you have, one area that's, weathers to a slope and another area that weathers to a cliff. It often is a function of its resistance to erosion, but also its resistance to chemical weathering. Then we also have physical processes such as water freezing and thawing that can enhance the erosion. I assume most of you guys have probably been to Enchanted Rock or at least seen pictures of it, where you have these big slabs of material sitting on the top of the rock that appear to be kind of suspended in space, where they've, look like they started to slide or part slid off of them, and there's just big chunk of rock kind of laying out there. Enchanted Rock is being broken down primarily through water freezing. It's primarily a function of water getting into very small pores in the granite that it's made of and freezing and opening up a little bit more, and then more water comes in there. The next time it freezes, it opens a little more, and eventually you open up cracks, and eventually you open up larger cracks, and eventually you fall off a huge chunk of rock from the surface of the overall mountain. And it's pretty amazing to think that Enchanted Rock is over 1 billion years old, and it's still being weathered down by the simplest of processes, which is water freezing and thawing. It's to me, it's amazing to think of something so simple breaking down something that has been there for so long. And then we also have, as we talked about before, when you get subduction, when you get volcanic changes and volcanism occurring in an area, the heat and pressure will transform the rock type. So when a rock is originally formed, it forms at whatever temperature and pressure it's stable at in that environment. And when you change that heat and pressure environment, sometimes the rock types, sometimes the mineral types will change. And so that is a significant metamorphic change that can happen that will change with the rocks we see around us. So now I'm just going to go through a quick little discussion of kind of where has Texas been in time. This is an interesting exercise using radioactive dating of rocks, using when a rock is formed from volcanism or from magma. When it crystallizes, it takes on the magnetic field signature of that it's involved or that it's experiencing at the time it crystallizes. And so you can, by looking at that magnetic field and by looking at the radioactive ages, you can kind of place the rock where it might have been during that time. So if you look all the way back to Precambrian time, 650 million years or so ago, this is Laurentia, which is the kind of proto North America. Laurentia, what
Possibly
became,
come over. Get 'em.
I'm sorry, was
I
there?
think they had them all the way down to Freeport.
Okay. So Laurentia is, as you can see in Texas, would be, you know, in this portion of Laurentia down here. It's very near the South Pole. So it's an Arctic environment. When you see these signatures on here, this is meant to depict an oceanic rift. So this was spreading, pushing these parts away from each other. And then these orangish lines with the arrows on them or the little triangles on them, those are subduction zones. So this is an oceanic plate coming in and subducting underneath this larger landmass that's forming here. So understand that, you know, and at this time, Antarctica was at the equator. Texas was very close to the South Pole. So we've kind of swapped places, if you will. If you move forward a few 100 million years, we've got the opposite. We've got Laurentia, the proto North America sitting up here. It's mostly still an ocean world, but there is the beginnings of a continental landmass forming up here, mostly up in northern Canada and up into the what's now today the Arctic. And you have over here the rest of all the continents on the world, pretty much forming the beginnings of Gondwana land, if you've heard of that term. It's all the continents kind of all massed together during this point in time. And then you come to Permian time, which if you think about the oil and gas development, a lot of that in Texas is in Permian aged rocks. And as you can see, this is all Gondwana has been put together, and this is now Pangea. Everything is pretty much all together in one landmass. And you see Texas is kind of sitting here with water over the western portion and up into the western US. And it's joined into South America here. It's joined into what will become the Caribbean, what becomes Africa over here off of Florida. And this, at this point in time, is kind of one of the foundations of how people figured out tectonics and the fact that what they originally called continental drift and then became plate tectonics, when they understood it better, is that they were geologists who were or scientists who were looking at rocks from Africa, and then they would travel across and go to South America and they would see rocks and say, wow, this looks just like what I saw across here. And they started kind of putting two and two together and realized that these were the same rocks and that these areas were together at one point and were spread by some mechanism. So that spurred them to start looking into, okay, why is this the way it is? Why does, you know, Northern Africa look like, you know, the East Coast of the US or things like that? You know, really thought-provoking moments for these guys that they weren't equipped to really understand, but it formed the foundation of what scientists following after them were able to come up with in terms of describing how these continents moved. And plate tectonics is really a very recent theory, if you will, very, you know, the 50s, 60s, 70s was really when we first started to understand how these continents were really moving. And before that, it was still much more in the air, and it was a very contentious theory between different groups of scientists who believe differently. Okay, so moving on to Jurassic time, the time of the dinosaurs, you can see the beginnings of the Rocky Mountains forming here. You can see Texas still is kind of in the water, at least West Texas is in the water here. Africa and South America are still together. And I want you to pay attention over time in the next few slides to India over here, which is currently joined together with Antarctica and Australia. and Asia, the rest of Asia is way up here. At this point, they're spreading, but over the next few slides, you'll see India start to move north. And I kind of want you to pay attention to that because it really drives home the point of what I was talking about tectonic relief and that sort of thing. So Cretaceous time, very important time for Texas. Texas is pretty much underwater. There's an inland sea going from what's today the Gulf all the way up through Canada and up to the Arctic. And this inland sea was relatively shallow compared to the rest of the oceans. And what was deposited there was a lot of limestone. So the Cretaceous limestones in Texas, the Edwards limestone, the Edwards Plateau, all of that area, and El Capitan, and the highest points in Texas, Guadalupe Mountain, are the reefs left behind from this limestone building ocean that was in the middle of the continent at the time. So if you think about the highest point in Texas being something that was once underwater, that really says something about the amount of water that was moving and the amount of ocean elevation change that was occurring and the way these continents were rising and falling due to the tectonic forces being exerted on them. And if you look over here back to what I was talking about before, this is India starting to move across the what becomes the Indian Ocean, but before this was called the Tethys Ocean. And if you look all along the west coast of South America and the west coast of North America, you're seeing this large subduction zone. This is what forms the Andes down here in South America. This is what begins to form the Cascades, the Sierra Nevada, all these volcanic ranges along the western coast of North and South America are all related to the subduction that is occurring this time and continues on to today. So we get into the Eocene, which is about 50 million years ago. You can see Texas is really starting to, North America is really starting to kind of take on the shape that it will continue to have through to present day. But you can see where we are in Houston area and along the coast, this water is still inland of where we are. We're still underwater at this point, and we're still looking at deposition in a marine environment, a shallow marine, but all the marine environment. And if you look, India has made it across the Indian Ocean, is beginning to collide with Asia, and we're starting to form the Himalayan mountains here. And the North Atlantic is opening up in the way that we see it today, but much narrower. East Pacific rise is still pushing subduction along South America and up along North America as well. We get to Miocene, which is about 14 million years ago. Texas is pretty close to what it is today. North America is all pretty well formed up. We're still adding some additional coastline here where we have subduction and volcanism occurring. Still seeing growth in the Andes down here. And if you look over here, India has now fully collided with Asia. And so those are a continental collision like I talked about before. And instead of one plate going under the other, you notice there's no subduction boundary shown here. These two plates are colliding. They're still colliding today. And everything is going straight up, pushing all that material that was between those two continents. Instead of one going under the other, it's all being pushed straight up in the sky. And the result of that has been that the tallest mountains in the world, Mount Everest and the rest of the Himalayan peaks, the top of those mountains are marine shales and limestones that were in that former Tethys Ocean and the crust that was laid down out there. That material is now at the top of the world. So when you think about topographic relief and you think about tectonics creating that relief, that's what you see. So this is the last ice age, and I show this just to, we've had, ice ages happening every 10 to 20,000 years for a long, long time. And so during those ice ages, a lot of the water on the planet is collected into the poles and collected into ice caps, but also into glaciers that stretched all the way down into North America and created the weight of those glaciers is what made the depressions that became the Great Lakes. Most of the major river systems that we see in North America are have much larger proto channels than what they're flowing in today, and those are mostly driven by glacial runoff and water from that ice melt, particularly in the Mississippi, but also some of the other river channels. And you can see the coast of Texas here is out at essentially at the continental shelf. It's the edge of the continental shelf instead of at the coastline of today. And so it's a very large change in sea level, and that happens periodically over and over and over in history. And so as that water goes from being onshore of us to offshore of us, we change from a depositional environment to an erosional environment. So when the coast of Texas is underwater, all the sediment coming down from the north and from the west in our rivers gets deposited on top of the land. And then when the sea level goes down, those same rivers and bayous that are coming through are eroding that material and trying to take it further offshore as the water flows. So just understand that almost the entire landform of what we see today in Houston and what we see along the upper Texas coast and even inland from there is formed by this constant back and forth of erosion, deposition. And most of what we see at the surface today is very young material geologically. You go out to central Texas, you get into Cretaceous limestone, you get into the Llano uplift that's, billion-year-old granites. But here along the coast, we're talking about sediments that were deposited in the last, 10 to 50,000 years, something like that. So very young material relative to what's in the rest of the state. And then modern time, you can see our coastline here is where it is today. The continental shelf offshore that was the coastline during the Ice Age is well formed. And in between, we have this kind of plateau that does some things to save us a little bit from storm surges, makes storms have a harder time gathering energy because of that shallow water instead of the deep, warm water farther offshore. So we'll talk a little bit more about how weather gets influenced here, but this is an important factor in helping us out, and also in our oil and gas production and things like that. Okay, so we'll talk a little bit about the ecological regions, and I put these two maps up just to kind of illustrate that the geologic map on the right looks an awful lot like the ecological map. And that's because what kind of rocks you have, what kind of topography is generated by those rocks, and what kind of chemical weathering and things like that and breakdown products you get are somewhat driven by the geology. You're not going to take a granite and weather it directly into a really nice mud or clay material. You've got to have an intermediate step where that granite's going to weather down into a coarse sand or a coarse gravel and then eventually break down further. But you're not going to get a dense gumbo clay forming over the top of the Llano uplift here in the middle. And so it kind of has its own ecoregion just because it's underlain by that granite that takes so long to break down. And then you look down here along the coast, and we're primarily looking at, like I said, very young deposition, Quaternary age deposition of sediment from erosion of all the rest of the state. Back. And then when you look out here in Big Bend, obviously it has its own depositional region because it has its own weather profile, but also its own geology out here. There's volcanic material out here as well, and it forms a kind of unique geology. But the other thing that I want to show you is the influence of rainfall on your soil development as well. When you look at the state of Texas, we have this enormous difference between the amount of rain we get in the east of the state and the amount of rain we get in the west, and that's driven by geology as well. Most of the rain that we get here in East Texas is driven by moisture coming off of the Gulf of Mexico. When we have cold fronts coming down from the north and from the west, in front of those cold fronts, you get a south wind that brings in all this moisture, and then the cold front squeezes it out, if you will, and rains a lot of it back out over the landform. So we can get, out in Beaumont and up into the northeast Texas, it's not uncommon to have 60 inches of rain in a year. Versus over here in Big Bend, you don't have the Gulf of Mexico down here to the south. So when those fronts come in, they're pulling wind from the south over the top of the Sierra Madre in Mexico, a very tall range of mountains. And so there's very little moisture on the backside of those mountains. When moisture gets driven up the side of a mountain by wind, the rain falls out. So you get into the Cascades, you see, basically, mountainside rainforests in the Cascades, because all the moisture coming off the Pacific is being driven up the side of those mountains. And as it rises, as that air rises and cools, it drops all the rain on the mountain. When it gets over the other side, goes out into eastern Oregon and out into Idaho, it's essentially a desert. It's a dry area that gets very little rain unless it gets moisture that comes in from the south or from the north around those mountains. And the same thing happens in Big Bend. The moisture that falls in Big Bend comes almost exclusively with the subtropical jet from Pacific, where it gets enough moisture coming across that it overrides the top of the mountains and still has something left. And so there's very infrequent, but in times heavy rain that happens out there. And that's what causes that landform, and it causes the soil development to be different. It's not a frequently inundated soil. It's not a frequently wetted soil. And so it has a different set of chemical processes that form it than what we have over here in the east. And so even where there's similar geology in parts of Big Bend or parts in West Texas to what's found somewhere further to the east, there will be differences in the soil formation simply because they get a different amount of rainfall, and that's controlled by the geologic controls of topography to the south and to the west. Okay, so here's my one slide on the hydrologic cycle. And what I want you to take away from this is not a map of anywhere specific, but it does do a pretty good job of depicting maybe what we have out in central Texas, out around San Antonio, New Braunfels, Austin, that area along the Balcones Escarpment. The Balcones Escarpment is a large fault system that runs all the way from up towards Dallas, all the way down, basically down I-35 and then out to the west of San Antonio. Once it goes through San Antonio, it kind of turns west and heads out into southwest Texas. But what that fault does is create an area where you have a large limestone plateau. Water falling on that plateau recharges the Edwards Aquifer, which then brings that water down into San Antonio, Austin, San Marcos, New Braunfels. And a lot of that water comes out at springs. So Comal Springs, what's the one in Austin? It's blank in my mind, but Comal Springs, San Marcos Springs, Aquarina Springs, whatever you want to call them down there. All those springs are being fed by a recharge that's falling on the Edwards Plateau and up into the recharge zone where this limestone is exposed. And then it transmits down into the groundwater underneath the cities. And San Antonio is hugely dependent on Edwards Aquifer groundwater, as are a number of the areas around San Marcos and those areas. We're undergoing great amount of development there. I say great in terms of number, not necessarily that it's good or bad, but there's a large amount of development happening there. And they're starting to run into a lot of water issues. And what I want you to take from this graph or from this map or figure is that there's always a connection. Some places it's faster, some places it's slower, but what we put on the ground is going to wind up in the groundwater eventually. What we put into our lakes can wind up in water. What we put into our groundwater can wind up in our lakes. a big issue that we're working on, and it's gonna be, you're gonna be hearing about it for the next couple of decades, probably, is what everybody's calling forever chemicals, PFAS, perfluorinated compounds that were used largely for firefighting and things like that, firefighting foams, but they're also have been used in all manner of products, Teflon linings for frying pans, Gore-Tex for jackets, things like that. These are chemicals that we've figured out can be disruptive to the endocrine system. They have other health concerns associated with them. And what they've also found is that they don't degrade. We don't have a way to degrade them in situ like we do pretty much every other chemical that you can list. The only way to treat them right now is to pull them out of the ground, run them through carbon, and clean them that way. And so it's the holy grail of my industry right now, is if somebody can find a way to degrade those chemicals in place without having to pump them out of the ground. They'll be making a lot of money, whoever can figure that out. But the end message here is understand where your water comes from. Here in Houston, a lot of it is surface water. So the joke is somewhat real that you can't drink the water in Houston unless Dallas flushes the toilet. A lot of the water does come down rivers from other cities. It gets treated, obviously, but we do fortunately use a lot of surface water. We do have some groundwater usage still. Most of our groundwater that is pulled out of the ground in the Houston area and the Chico Aquifer fell up in Montgomery County, up in Polk County, places further north, probably hundreds or thousands of years ago. In the Edwards Aquifer out in San Antonio, some of the water coming out of the wells there probably fell last week. The aquifer out there gets recharged much more quickly, and as a result has the potential to be contaminated much more easily than the water here around Houston, but we still managed to do it here in Houston too. I worked on plenty of plumes that were 200 and 300 feet deep from contamination here in Houston. So just again, it's all related, it's all connected. So be aware of where, if you're going to put something in the ground, be aware of where it's going to go. If you're going to pull something out of the ground or drink something, be aware of where it's coming from. Okay, so last thing before I kind of go into the case studies here, I want to talk a little bit about how does alluvial systems, river systems, bayou systems, how do they deposit material? When you think about flash floods, when you think about fast moving water, the faster that water goes, the larger the size of the material that can be transported. So, in the bayous here in Houston, most of the time they're just going to transport a little bit of clay and mud, very fine particles that can be carried by slow moving water. When we get a flood and you get more water movement and a faster bayou flow speed, you can pick up some sand. You might even pick up a little bit of gravel and move that along. And then if you go out west and you see, rivers flowing down the side of a mountain, or you see flash floods, huge volume, huge speed of the water there, that can pick up boulders, that can, really transport a large amount of material. But the end result of all that is when the water is carrying that load and it slows down, the first thing it drops out is the larger material, and then it drops out the slightly smaller material. And then when it comes completely to a stop, eventually over time, it will drop out even the smallest clay particles. And so here in Houston, what that does for us is when you have water flowing through a bayou and you get a flood, when that water, it starts carrying a lot bigger load of sediment. When that water goes up and over the banks, it runs into trees, it runs into houses, it runs into other barriers that slow it back down, and you start dropping out material. And the further you get from the bank of the bayou and the slower the water moves, the lighter the material you get dropped out. So when you see a lot of our bayous around town, you'll see these kind of banks next to them that go higher than the surrounding land and then come back down. And in most part, that's not a man-made levee that's formed. It's simply an overbank deposit where sand and gravel got deposited immediately, and then clay and other things deposited further out. And so you can get a natural levee built along the side of a bayou or a river when you get enough floods happening that way. And it's that fine grain material, the clays and other smaller particles being deposited out here that make river sediments or river bank sediments such great agricultural lands. So we have a lot of bayous, we have a lot of floods in Houston, and it's a reason we had a lot of great agricultural land in our area. Now we've covered most of it with subdivisions, but it still remains good agricultural land where it's present. And then I mentioned where maybe in the past we had more water moving, whether it was because this area was farther from the coast or whether we had ice and other sources of water further to the north and to the northwest. But a lot of our rivers have an original floodplain that has been cut down into a smaller bayou. And so those of you who have ever ridden the MS 150 or driven out to Belleville from Houston on Highway 159 will see this. When you come down 159 from 359, you drop down a couple of different terraces. You cross the Brazos River, and then when you get to Burley, you go up a terrace and you go up another one. And those are the first two big hills that anybody encounters riding their bike from Houston to Austin. And that's when you find out who's trained for the ride, because those are not insubstantial hills. They're not insubstantial elevation relative to all the flat terrain around Houston. So if you ever drive out that way, just pay attention as you're coming towards the river, because these terraces are much wider than you would think. And it's generally when we have floods, we flood the inner terrace, but every once in a blue moon, like Harvey, we get enough of a flood that we flood this larger terrace out here. And so a lot of the homes are built up on the hills above the river suddenly are flooded because they're still part of that old river floodplain, but they're just on a higher setting than the others. So keep that in mind as we talk about erosion and as we talk about where we build things and where we see deposition. So lastly, when you talk about delta formation, this can be a river flowing into a lake. It can be a river flowing into a big slow moving bayou. It can be a river flowing into the Gulf of Mexico. But what happens, as I said before, is when that water reaches that point, it slows down. And when it slows down, it starts dropping out sediment. And so you get all these areas where you've got a big pile of sediment formed up. And the water still is coming down, still has to find its way through. So it's going to start running through these channels, and what they call distributary channels. And over time, as it does that, it'll suddenly form a block here where, okay, the sediment's all dropping out here now because it's coming down this channel, hitting the Gulf and stopping. This one will get plugged up. Well, now the flow is going to go through this one. And it's going to keep going back and forth and picking different channels over time, until something happens like humans coming along and building levees and jetties and things like that. And then we say, okay, we've picked this one channel, this shall be the channel from here on out. And in the New Orleans area, as I'll talk about during one of the case studies, that has some fairly significant implications when you do that. When you say, okay, we're not going to allow this water to go over here and recharge all this area with sediment, rebuild all this area with sediment, this shall be the channel. Well, suddenly you've got one channel sticking way out to the side, and it's it becomes a suck that takes all your sediment that would be replenishing your land surface, and it takes it out and deposits it offshore. So it has some implications. We'll talk about it here in a few minutes.
William, I have a question about that slide that we just came from. So is the delta, is that considered where the deposition starts?
Yes and no. I mean, the deposition is going to happen anywhere that you have water slowing down. In general, what happens is these deltas progress kind of seaward, where you get, delta will initially form even with the coastline. You'll get a little, this one kind of shows it, you get a little bar forming right here where you have water coming through a marsh. Over time, as this gets built up, you get further out and you start seeing kind of a lobe forming. And eventually what will happen is, you'll get enough sediment built up in this lobe that the river will say, hey, it's easier to go overland over here and make a new channel come out here, and then you'll start forming a whole nother lobe. And in the case of the Mississippi, what the Mississippi really wants to do is go down the Atchafalaya River. If we had allowed it to do so, the vast majority of the flow of the Mississippi would be flowing down the Atchafalaya River today. Right now, I think the number is we let about 30% of the flow go through the river control structure. But you know, all it would take is one errant barge or one you know, really bad maintenance screw up, and we could lose the river at that point and basically have the Mississippi trying to flow down the Atchafalaya, and it would take a pretty Herculean effort to get that river turned around, and if we ever let it get to that point. And as John McPhee says, I'm betting on the river, but eventually it's going to happen. But you know, whether we have control over it or not is a fair guess. When it happens, you know, who knows? Did that answer your question?
It does, thank you.
Okay. So again, just to show, when you look at these bars that form, eventually these become barrier islands. If you have enough sediment coming down, if you have the washing of the fine silt out of it by wave action that deposits that silts and clays and muds out here farther offshore, you get these sand islands. And that's what Galveston, that's what Matagorda, you know, that's what Padre Island. These are all bars that have basically formed and protect a marsh and bay system behind them, where the water's coming down at velocity and then slows down and meets the Gulf. So that's the essence of how our landforms, and especially our coast, are formed today, is just that constant transport of sediment. And if you interrupt that deposition of sediment here and channelize it to where it shoots it all out here, you're no longer replenishing these marshes. And that's part of why Louisiana's barrier islands have disappeared, and why their marshes are disappearing, is because all that flow from the Mississippi that replenished them has been sent out to the deep water instead. Okay, last thing, I think, talk just a moment about soil. So a geologist's definition of soil is that loose stuff above the rocks that prevents me from seeing what I want to see. You know, it's the stuff that gets in the way. And you'll see on geologic logs, a lot of times they'll log the top, you know, 10, 30, 40 feet, 100 feet as UDS, undifferentiated sediment, is what they're saying. I'm not even looking at it. I'm not going to log it. I'm not going to describe it, because I don't care until the drill gets to the rocks and I start seeing the things that I want to see. A lot of times they won't even log it. So when you look at a drilling log, that may be what you see. And then for soil scientists, they're a little bit more interested in it. And so their definition's a little bit more complicated. And if you take soil science at Texas A&M, when you used to take it from Murray Milford, he would make you memorize this definition, and that was your first pop quiz in the course, was to regurgitate this definition word for word. And just so you know, good rock gone bad was not an acceptable substitute for the definition of soil on that quiz. But I say this all kind of in humor, but the reality is that a geologist may be looking at hundreds or thousands of feet of profile, very deep boreholes, very deep excavations, you know, cuts and whatever. And so they're looking at large scale features. The soil scientist is looking at factors that involve plant growth and agricultural capabilities and surface engineering features. And they're going to look at the top 60 inches, the top 5 feet. They're going to dig a 5-foot hole, describe what's in those top 5 feet in excruciating detail. There may be multiple profiles, multiple different layers, but they're going to get into very small level details that the geologist is going to ignore. And so when you look at a geologic map of Houston and see all the features defined as Beaumont clay, that's a kind of overriding thing for a very large formation of soil. But the geologist doesn't get too deep into what it is. The Beaumont clay is described as sand, silts, and clays interlayered in alluvial formation or something like that, a very generic discussion. Whereas if you look at a soil science map of Houston, they're going to have all different varieties of soil units, talking about what's the slope on the surface, talking about, you know, the different surface layers and things like that. So it's a much more involved and much more detailed look at the very shallow surface. So when you go to look at a geologic map, look at a soil science map, just understand they're talking about different things. They may use the same name. There is a Beaumont clay formation that the soil scientist will describe, but it's not necessarily the same as the Beaumont formation that the geologist is describing. Okay, so just a couple things that'll lead into the case studies, and then I'll give you a chance for a quick break. How does geology affect Southeast Texas and the Gulf Coast? We have oil and gas production. There's a layer called the Luan Salt that was formed during one of those times when the ocean was very far out to sea, or when the coast was very far out to sea, and we had a salt formation laid down here along the coast. And that salt creates salt domes and embedded salt that allows it to trap oil and natural gas in the formations around it. And so those are things that geologists learn to look for and be able to drill for the net oil and natural gas there. And then we also use those salt domes for secure storage of gas and liquids. It's a very great medium to be able to wallow out a cavern or hollow out a cavern in a salt dome and then be able to pump either gas or liquid into it. And it does a great job of holding on to it. So well, in fact, that we use it for the Strategic Petroleum Reserve, both here in Texas and over in Louisiana. We put large quantities of petroleum down there and can pump it back out, and you just have to take a little salt out of it in order to be able to refine it. As I said before, we've got good soil for agriculture. We have all these overbank deposits that periodically refresh the nutrients. And until we started channelizing bayous and trying to stop these floods, we get this periodic refreshing of nutrients in our soil from floods. And I know everybody, you know, doesn't like the periodic refreshing of nutrients in their house from the floods, but it is actually very good for our soil to have that periodic flooding. And then our barrier islands will protect our ports, protect our facilities that we build inland, as long as we protect them too. And I'll talk about that in the case studies. Negatives, we get subsidence and faulting. Because we're on an alluvial sediment, that sediment is constantly trying to settle and fall, and it happens in a differential way at times where some of it's falling faster than others, and so we get faults. These aren't tectonic faults. They're simply differences in settlement rate that cause linear features that are called faults, and where you can see damage to structures and damage to roadways if it's settling fast enough in one side or the other. I'll show you a little bit about that. We also have faulting caused by the uplift of the salt domes. The salt is lighter and kind of has a unique property that allows it to flow. So you get a lot of sediment weighted down in areas. The salt's going to try to push up between that, and it will uplift areas of soil above it that can cause faulting as well. And then we get subsidence, where when you pull enough groundwater, you pull enough oil and gas out of the formations, those formations will shrink vertically and be compacted more easily by the material above them. And so you can have the land surface falling, what we call subsidence, because of that. And then everybody, the joke in Houston is there's two kinds of house foundations in Houston, those that are cracked and those that are gonna crack. That's because a lot of the clay materials that are in that alluvial soil will swell up when we have moisture, excess moisture, and then they shrink when the moisture dries out of them. And so that constant motion back and forth can damage foundations and other infrastructure by causing weakness in the underlying foundation and causing it to crack. And then we have a kind of a positive negative situation, right? So the proximity of the Gulf, really positive for us because it increases our rainfall and our humidity by having that ready source of moisture right there that's really good for agricultural production. That humidity and that water availability also makes our winters warmer by buffering the temperature, makes the summers a little bit cooler closer to the coast. In absolute temperature, feels like maybe not so much. But it also is protective of, you can grow plants in Houston that you can't grow further west away from the Gulf, simply because the Gulf is buffering that temperature and making it more stable for that. And then we have the negatives of the proximity to the Gulf, which is that it increases humidity. A lot of people don't like it. I grew up in it, so I really liked it, but it still can be a bit much at times. And then that increase in rainfall can be a bit much too sometimes with hurricanes and flooding. So it's a positive negative situation. I think overall it's generally a positive, but some ways it can be negative. All right, so does anybody need a 5-minute break? If not, I'll jump right in and keep going, but if anybody wants a break, let me know. Okay, I see at least one hand waving, so go ahead and let's take a 5-minute break. I've got 9:20, we'll be back at 9:25. How about that?
Can I ask you a question, William? When we drove up to Alaska about 10 years ago, one of the things I remember about Mount Denali is they said it's uniquely a slab of granite surrounded by other rock that is not granite. How does something like that happen?
What is usually the case, it's the same kind of thing that formed Enchanted Rock, is that you
Okay.
have rising magma or rising, magma is lava that hasn't erupted to the surface. So it's magma coming up, forming like what they call a pluton, which is a body of magma below the surface. And it can come up and basically cool below the surface.
Okay.
And crystallizes. It cools very slowly, which is why you get very large crystal sizes up in Enchanted Rock, for example, because it's just like rock salt. If you let the rock salt dry, or rock candy, if you let it dry out really fast, you get a big powder. If you let it dry out really slow, you get some larger chunks of it. It's the same thing when you cool crystals of a magma. The faster it cools, the smaller the crystals, and so you get. But what happens is you get that pluton solidifies. Eventually it stops erupting and the magma cools off, solidifies, and forms a big plug of granite or diorite or some other material. And then over time, weather erodes that looser soil off the top of it. And since it's more resistant, it's left behind. So you get a big chunk of rock sticking out, and then you've got all this stuff around it that's easier to erode. And so in Texas, we get like the Pack Saddle schist, the Valley Springs gneiss. Those are metamorphic rocks on the flanks of these things that were affected by that temperature and pressure of that magma. They were a different type of granite or a sandstone or a shale that was there when that granite was being pushed in, and that they transform the rocks around them by changing the temperature and pressure profile. So that's how we get those metamorphic rocks. If you look on the geologic map, you'll see a big pink section that's the Town Mountain granite, and then you'll see a ring around it of these metamorphic rocks. So the Pack Saddle schist, the Valley Springs gneiss, and you also see the younger granite out there, which is not kind of oxymoronic, that it's the older granite that the Town Mountain granite was uplifted into. So, but it's named after somebody named Younger or something like that. So, but it's actually the older granite in terms of time and age. So.
All right. That's perfect. Thank you.
Okay, I'll be right back. Okay, so I've got 9:26. I don't see a couple of the people back that were showing up, but I'll go ahead and get started here. I think everybody will be able to, that isn't here will be able to pick up. So these case studies, before I get started, let me just take a sip here. These are kind of things that are happening around the Houston area that either are happening to us or that we're doing to the landform. And so people like to think about geology as looking at rocks. Every time I told somebody in college that I was a geologist, say, "Oh, you look at rocks." Well, I live in Houston. There are no rocks, so I look at what's called geomorphology. What is the landform created by the geology and by the geologic process? So you can go through multiple classes in geomorphology, but most of what we see in Houston is stuff related to alluvial sediment transport, deposition, erosion, things like that. And so that's the things that affect us. And I'm going to talk about a few things that are going on. A few of them are current projects that are in the works. And I'm not trying to tell anybody how to think on these. So don't take anything I say as, I'm the smartest guy in the room and I have all the answers. I don't. But a lot of these are kind of value judgments of what do we value less, and because there's some trade-offs that are going to come with all of these projects. So I'll talk about that, but just understand that, I'm not, if you're involved in it in one way or the other, I'm not trying to say anybody's right or wrong. I did this talk and had one lady, I talked a little bit about the subsidence, and her takeaway message that she told somebody else apparently was, I found out that, that oil and gas is all bad because they cause subsidence. And that's not the point of this talk. There's undeniably, some things that cause some of this stuff, but it's not, I'm not making a value judgment on anybody for it. So please don't take it that way. Okay, with that disclaimer said, this is the part that she was talking about, that this is the Goose Creek oil field, kind of in the same vicinity as the Goose Creek Nature Center area, right along 146 there near the Fred Hartman Bridge, Baytown area, early 1900s. So look at all these oil wells, right? Wow, that, they must have really been, getting a lot of oil there if they had all those oil wells way back when, right? Here it is in the 1970s. Still a lot of oil wells. We used to drive past this every other weekend going to my grandmother's house when I was a kid. And we used to joke with my dad that you could walk across the bay going from platform to platform and never hit the ground or never get your feet wet. And it wasn't far from the truth. There's a lot of oil and gas that was drawn out of the ground over in this area. And that situation or scene has been kind of repeated all around the Houston area, both with groundwater and with oil and gas for many, many years. And the result is that we've caused a great deal of subsidence. I mentioned that this whole area is kind of naturally subsiding to some degree, but this is very rapid subsidence relative to what you would see in a geologic sense. And this is from 1906 to year 2000. And these contours are in feet. So if you look over here around where Goose Island is, you're talking about 10 or 12 feet of subsidence. That entire area in 1906 was 12 feet higher than it is now. When you look around Exxon Baytown here, it's about 9 feet of subsidence in that general area. You get in here along the ship channel, that's 10 feet of subsidence, where the plants, mostly in this area, it was plants pulling water for their processes to use in their various processing and refining. So there's 6 feet of 10 feet of subsidence there. And then right here around the wastewater or the central water plant for City of Houston, when they were using groundwater before they put in Lake Houston, they pulled an awful lot of groundwater out of the ground here, and they had about 7 feet near downtown. And then down Texas City, you can see there's about 6 feet. Kemah area, Clear Lake, you're looking 5 to 6 feet of subsidence. And all of this is mostly from the removal of groundwater and the removal of oil and gas from the relatively near surface. And so if you think about the impact of that, basically the Brownwood subdivision in Baytown became unlivable because there was so much subsidence that it was flooding all the time. FEMA bought them out, and that's now where the Goose Creek Nature Center is. is in that former subdivision that basically sunk to the point that they could no longer use it. And, what would the Kima Boardwalk have looked like after Hurricane Ike if it were 6 feet higher than it is today? So we now have the Harris Galveston Coastal Subsidence District that is pushing as much as possible to get people off of groundwater and to stop pulling groundwater out, especially in areas down towards the coast, but even all the way over into West Houston, we're now mostly using surface water because we're trying to minimize the amount of subsidence that's occurring, and all of those things have implications for flooding and have implications for storm surge with hurricanes and things like that. So the more we can reduce the subsidence, the better off we are. So next time you're cursing the fact that your water has a little bit of something in it from Lake Houston after a big storm or something, understand that you're drinking the lake water mostly because we're trying to stay off of the groundwater and minimize the subsidence. And then this is an interesting story that goes back to my dad's time at NASA. He had a buddy there at NASA called Ewell Clanton, and when they finished training the astronauts in geology, they had this big science group there. And my dad left to go be a mining geologist, but several of the guys stayed with NASA. And Ewell Clanton started using Landsat imagery. When they put up Landsat, they had this great imagery, and he was looking and saying, hey, you know what? You can see these faults around Houston using Landsat. And so he started mapping up some of these faults. This is the area down around Ellington Air Force Base, Hobby Airport. I-45 goes pretty much kind of right down through the middle here. And there's a series of salt domes that are around the Hastings Salt Dome and several others. And there's a series of oil fields. So between the rise of the salt domes and then the subsidence occurring from removal of oil and gas around them, there's some significant faulting down there. And if you drive down I-45 right before you get to Dixie Farm Road, there used to be a little bump, about a 1 foot or so rise in the pavement, or drop, depending on which direction you're traveling. And that's one of these faults running right across I-45. And when they redid that whole section, they put in some additional joints there. And so it's not nearly as noticeable, but you used to be able to see these faults when you went through there. And you can go and look over off of, I guess it's called Clear Lake Parkway now, but FM 2351. If you look out into those oil fields, you can see some lines of trees that aren't necessarily related to a fence line. And those lines of trees and bushes are along these faults where the soil has been disturbed, and it makes it easier for water to inflow, easier for the roots to grow. And so it's easier for trees to grow there. And so you can see the effect of these faults. But what Ewell did was he said, hey, look, we can see where these faults are. We should, talk to the developers and talk to the city planners and make sure we don't put infrastructure there. So he went to the folks in Houston and went to Harris County and started talking to developer groups and saying, hey, we can map all these faults. We can see where these are, so you don't build subdivisions or, commercial complexes on top of them. And they were so grateful to Ewell that they went to his bosses at NASA and said, shut up, stop talking about it. We don't want to hear about it. You're ruining our development. We don't want people being scared that they're going to have faults under their houses. We don't want to hear about it. And so Ewell's bosses came to him and said, Ewell, you're kind of ticking off the local politicians. You're ticking off the developers. We don't need that right now. So go find something else to do. So this got taken and set aside and not used and for a long time. And I went looking around back when I was doing this talk a long time ago. And in 2006, the Harris County Flood Control GIS department won first place in best overall in a GIS map competition. And the map they made was principal active faults in Harris County, Texas. And their text associated with it was talking about how they were making Harris County aware of geologic formations and active fault lines and allowing places to determine suitable places to locate their infrastructure. And before you were allowed to look at this map, you had to click off of this disclaimer that the data was supplied by the U.S. Department of Agriculture. And the reason for that was I'm sure they got inundated with people calling up going, you mean there's a fault under my house? They said, no, look, we just made the map. It's not our data. talked to the USDA, and now when you go look, you can't find this map. They're so proud of this award-winning, competition-winning map that you can't find it on their website. At least I couldn't last time I looked. So it's still a topic that we have information about, and it's still one that's not super popular, I don't think. So this is the map in large scale, and you can see down here at this along Gulf Freeway, those are all the faults that Ewell was mapping, and he did a pretty good job of mapping them out. And then one that you can really see if you ever drive through that area of town is this Long Point fault, and you'll see it on another slide here in a minute. But if you drive down Willcrest, right before you get to Berry Knoll, you get about a 3 or 4 foot drop in the pavement. They've repaved it again, so it's a little smoothed out. But if you look back through the subdivision, you can see that that fault goes right through people's backyards. I'm sure people's houses were impacted by it. So there's definitely an impact on subdivisions and on housing areas by this entire fault. And it's a fairly long-lived one for what you see around Houston. And so now there's a gentleman by the name of, and I apologize if anybody knows him, but I'm going to butcher his name, Shubham Khan at the UH Department of Earth and Atmospheric Sciences. And he's got grad students that have recently been out using LiDAR images to do the same thing. And so this is that Long Point fault mapped on LiDAR. And you can see this little rectangular box here is a groundwater retention basin, stormwater retention basin. And this fault line that runs along is very visible on the LiDAR, goes right through the middle of that thing. Now that's not, you know, all that's going to do is make the stormwater maybe infiltrate a little better. But if that were a sensitive building or, you know, a school or something like that, that we had built right over the top of this, it would have potential, you know, concerns for what that might do. And I mean, you could see all these little streets back in here that show up on the LiDAR. These are all homes. And so that fault is running through yards, running through homes, running across Gessner. I'm sure there's businesses up and down here. So we have the ability to use these, we just haven't. And it's mostly because the developers don't want to be troubled by it. They just want to sell the stuff. So I'm a little hard on the developers there, but it's something we should be more cognizant of, and most people in Houston aren't. So. All right, so this one goes a little bit away from Houston, but it has some relationships to what we're talking about in Houston, as you'll see in a minute. But I'm going to talk about the channelization of the Mississippi River and give you a geologic basis for why one of the levees failed during Katrina. So the Mississippi River, they started building levees back in the 1700s along the Mississippi River. Early 1700s, people were using shovels and wheelbarrows and building levees to protect farmland along the river in that rich, fertile soil. And eventually they were required by state law to build their own levees to protect land. They basically said, if you're going to work down there, you got to build your own levee to protect yourself. And in 1879, we created the Mississippi River Commission. And the main part of that, their mission was to control floods down in the southern portion of the river that were causing problems with river navigation, you know, commerce coming in and out of the New Orleans area and that sort of thing. So they created a commission to oversee the flood control in that area. And they had that commission had a levees only policy. They basically said, we're going to basically channelize this whole river with levees to create a self-cleansing river system. We're going to scour out that channel by constraining this flow so much that it scours the channel and keeps the river open for us, which was great when you were having an issue with dredging. You remember those distributary channels we talked about down in New Orleans? When you're having to dredge those all the time because the ships don't know which ones are filled with sediment from month to month. It maybe is a great idea, but when you start doing that to the entire river system, it creates a series of problems. And by 1913, so from 1879 to 1913, they extended control of the river all the way up to Rock Island, Illinois. So it's no longer just a Mississippi navigation thing down near New Orleans and flooding area down there. It's now basically control of the river all the way to Illinois. And this is kind of the result of that. This is a series of Mississippi River levees. This is from a professor over at Missouri University of Science and Technology. And this doesn't even show everything since 73, where we built additional levees on top. We put flood walls on top. We put sheet piles down inside to support those flood walls, particularly down in the New Orleans area. And so you can see this is not a one-time thing. This is okay, we're going to build a levee. Well, that didn't work. We're going to build another levee. Well, that didn't work either. And John McPhee, in a book called Control of Nature, has a great description of this, where he talks about over time, every time there was a big flood, the politicians would ride in on a wagon and stand on the back of the wagon, or ride in on a train and stand on the back of the train, or come in on a helicopter and get off the helicopter every time there was a flood, and tell everybody there, oh, we're sorry for this terrible natural disaster that's afflicted you, and we're going to come back here and rebuild better than ever, and we're going to make sure this never happens again. And so they build another series of levees, and then, somewhere, 10 miles downstream, they'd be there 5 years later telling them, oh, this is a terrible disaster that we foisted on you by shuffling all this water to you. And we're going to build the levees better and bigger than ever before. And it's just this ongoing saga of, let's build bigger, let's build bigger, let's build bigger. And we're constantly still trying to control all this water. And every time we, it's like a slinky or something. Every time you squeeze it at one end, it's going to pop out somewhere else. And so that's all we're doing to the river with most of these levees, still trying to keep this self-scouring system. And as I said before, the ultimate endpoint of that is that this is the original Delta fan that was around New Orleans. And when you take this one channel and say, okay, this shall be the channel, instead of letting it go out here or letting it come down here, you can see these old abandoned deltas here. When you take away the flow to those channels and say, this shall be the channel, you end up pumping out everything out here offshore. And so all of these areas, just like Houston and just like, the marshes around Galveston, these are all still subsiding. Just that natural compaction of the alluvial sediments over time, these are all still subsiding. They're still sinking. And when you take away that replenishing sediment that would be deposited in these areas, they go away. So these were barrier islands at one point that would protect New Orleans. Now they're tiny little sandbars, because that area has sunk underwater. These once thriving marshes here are sinking and sinking deeper in the water, and they're not getting that replenishing sediment. And so we're not seeing that change that would keep those areas revitalized and keep them protecting Mississippi, or the Mississippi River, and particularly infrastructure in New Orleans. So this is kind of a by deciding we're going to build somewhere that it floods, and then saying we're going to control the river to keep it from flooding, we've created a whole new series of problems. We've created an entire city below sea level now, surrounded by levees that have to be maintained and improved and constantly worked on. And so it has it certainly was a boon to the commerce to do this, but it's also come at great cost in terms of flooding and in terms of the maintenance and the management required. So just that's not a judgment, it's a value system, is the way I like to say. If you value that enough, then it's worth the money and it's worth the cost. But if it's not, the story's not over for New Orleans. They've built a new inner harbor navigation canal and flood wall, and it's, my company built it, so I can't say anything bad about it, but it did a good job. It's doing a good job so far, but I mean, it's not the end story. The area is all still subsiding, and it's still, eventually that will not be enough if it continues to subside. So there will be other things that will be needed. And now I'm going to talk specifically about one of the Katrina failures. If everybody has memories of what those images from Katrina look like, and there were a series of canal breaks and breaches in the levees and overwash in some of the areas. The one I'm going to specifically talk about is this 17th Street canal break, which is right here, got a blue and a red star on it. And this was specifically caused by a failure of geology or a failure of geologic understanding. Everybody has this iconic image of the Corps of Engineers in there dropping sandbags in trying to fix this breach so they could start pumping the water out. But what most people don't realize is that this flood wall that was on top of here, that flood wall did not fail in the sense that you would think. It did not topple over and fall backwards. The entire levee that it was sitting on slid back like it was on a conveyor belt. And if you look at this next photo, you can see this flood wall is still, it says toppled back up here, but it's actually still standing up. It's still standing upright on top of the levee. The entire levee slid back 49 feet. And the reason for that is that when they put these flood walls in, they said, okay, when we put enough water pressure up here, we could charge this marsh layer that's in the subsurface with enough water that it would make it weak and the whole levee would fail because of it. So we're going to put in a series of sheet piles along the entire length of the levee to stop that water flow. And when they were targeting these sheet piles, they drove down the top of the levee drilling borings. And at boring 64 up here, they were targeting this gray clay. This CH symbol is a shorthand symbol for this fat clay, or it's clay with some structural capability. And this marsh was what they were trying to seal off. And on this one boring, this layer was called gray clay CH with marsh interbedded or something like that. And it was a mixed zone of clay and marsh. And when somebody was drawing up their cross section of how deep did these sheet piles need to be, they saw gray clay CH and stopped reading. Didn't read that it's intermixed with marsh layer, and didn't mix that it wasn't full clay with silt and sand lenses. Instead, they dropped the sheet pile just below the edge of the marsh and into that intermixing zone. And when the water level during Katrina got near the top of that levee, and top of that flood wall, there was enough water pressure to push water down into that intermixing zone underneath the sheet pile and lubricate this weak strata behind the wall. All the pressure of that water was pushing downward onto this section of the levee. And when it hit that weak strata, it sheared. And basically the entire levee slid backwards by 49 feet, allowing the water to run in and flood New Orleans. And so a simple thing, not really understanding the boring log that you were looking at, and accordingly making an engineering decision that was flawed because of it, is what caused that particular levee break and what caused that section of New Orleans to flood. So very simple mistake, probably had an entry-level geologist or engineer looking at those boring logs, and it had enormous implications for the people in New Orleans during the flooding in Katrina. Okay. So case study number 3, Hurricane Harvey and the ever-flowing sand. Sounds kind of like a Harry Potter novel, right? So this came out of a question that came about from Hurricane Harvey, where somebody came and said, where did all the sand come from? Buffalo Bayou got full of sand, everything around Kingwood was full of sand. Where did it all come from? So we'll talk about that. So when you look at downtown Houston in particular, and the White Oak Bayou and Buffalo Bayou watersheds, they drain a significant portion of the west. And I mean, this Olive Addicks Reservoir and Barker Reservoir also feed Buffalo Bayou. And all of this water is aimed at downtown. And so you remember what we talked about with flowing water picks up a load, fast flowing water picks up more of a load. And you think about that entire watershed during Hurricane Harvey filled with water, moving very fast, highest water levels we've ever seen on these bayous. And it's going to pick up a large load of sediment, right? And then you look at where Buffalo Bayou comes into downtown, comes across, meets White Oak Bayou coming down, goes right into this little choke point right here, right by U of H downtown and some of the areas around that. And so you've got a very constrained flow channel. This is what White Oak Bayou looked like. This is what Buffalo Bayou looked like coming into downtown. And so got all this water, very loaded with sediment, right? It hits that choke point. What's it going to do? It slows down, backs up. What does water do when it slows down? It drops out the sediment load, right? This is Buffalo Bayou Park after Hurricane Harvey. Huge amounts of sediment brought in by fast moving water coming down Buffalo Bayou, suddenly had nowhere to go, stops, drops out its channel load. So that's the simple part of it. I mean, obviously up to the north around Kingwood, there were things like sand mining and things that made more sand available for transport along the river channels. But the overriding thing was that there was enough water flowing that it, was transporting more load than ever before. But the Corps of Engineers came along, and one of the issues they had was that these two stormwater retention basins, the reservoirs out here, Addicks and Barker Reservoir, were built specifically in the past to protect Allen's Landing in downtown, which were sensitive economic features. And they were trying to contain water from the west side of Houston from rampaging down Buffalo Bayou and flooding out downtown. So they built these things. And this will become a theme in the later sections here in a minute, but they have a design flood. So they said, this is the biggest flood we think these reservoirs will have to contain. And they bought enough land behind their reservoirs for that designed storm. And then they built the reservoirs over that. Their engineers always overbuild a little bit. So they built the reservoirs taller than they needed to be to control that that design storm. And when they did that, well, during Hurricane Harvey, it was more than the design storm. And so they flooded huge areas behind these reservoirs that they didn't own. And they got sued for it. And the Corps of Engineers has had a judgment against them for a significant amount of money, as I recall, saying they're responsible for flooding land they didn't own. And they also had people, when they opened those floodgates up to try to stop that from happening, they flooded people down here along Buffalo Bayou that were previously not flooded. And so those people were suing the Corps of Engineers as well. And so the Corps of Engineers' reaction to that was to form a task force under the dam safety group. And the idea of that task force, their mission was to protect the dams. Basically allow them to operate this dam in such a way that they could run full flow out of their dam without impacting people along the Buffalo Bayou watershed with a flood, and also allow them, and that by allowing them to release fully, it would keep them from flooding the places they don't own behind them. So they're saying, okay, the answer to this problem is to protect the ability to operate our dam, which was designed to stop them from having to release full flow to downtown. So they're going to change this channel along here to allow the water to flow fast enough that it will not affect their dams, right? Not affect the people when they release their dams at full flow. That's their design that they came out with for Buffalo Bayou. Completely channelized, 70-foot wide bottom channel, mixed slopes on the side, ditches at the top. Basically, we're going to tile this whole side and then put some grass over the top of it. 200 and something feet wide, I think, was the final section. So all through Terry Hershey Park, all through Buffalo Bayou Park, all the way down, we're going to take 210 something feet or something like that, completely turn it to grass and make it a channel. So that's going to leave the White Oak Bayou confluence that we talked about, that was this choke point, is outside the project area because it stops at the western edge of downtown. Not inside the project area. There's no habitat left for alligator snapping turtles, of which Buffalo Bayou is terrific habitat for them. Doesn't leave anywhere for sediment to deposit prior to reaching downtown. In my mind, it destroys the legacy of Terry Hershey and eliminates some of our last and best undeveloped riparian habitat along those bayous. And the reason for doing this is to protect the dams that were originally built to protect downtown, right? So we built these dams specifically so we wouldn't have this rush of water coming to downtown. Now we're going to rechannelize the whole bayou so that we can open the floodgate on the dam wide open, send all this water downtown. But we're not going to do anything about this choke point in downtown because it's outside of our project area. So their project ends where this wave of water hits downtown and somebody else's problem to fix downtown, right? So, have we learned a lesson there? Are we, would it have been better to buy some houses behind these reservoirs? Would it have been better to, open up a choke point in downtown? Is a tunnel better? They got enough comments that they're going to go back and relook at all this. But I think in my mind, the answer is not this. I hope it's not this, because I don't think this is the best means of doing what we need to do out there. All right, so I've got one case study left. It's 9:57. If you guys are willing, I'll keep talking. If you'd rather I wrap up and take questions, let me know. But I think this is one that people are likely to be interested in as well, given the recent news stories. But unless somebody raises a hand and says, stop, we've got to get off of here, I'll keep talking. Probably about 5 minutes, hopefully. So talking about the dunes along the coast, we mentioned the barrier islands. I showed you the ones that kind of had disappeared off of New Orleans there. We have a great system of barrier islands along Texas, and they protect our coastline, they protect our ports and some of our coastal cities. And we've done a good job in some areas of protecting them. The Padre Island National Seashore is forever protected now, hopefully. And we've got a long series of dunes down there that are in really fairly pristine shape. And if you've never been down the North Padre Island, the dunes down there, the first line of dunes are often 20 to 25 feet high. Huge dunes, very well vegetated. There's swallows nesting in them and things like that, but very well-developed dunes. This is what it looks like from above. You can see that first line of dunes out here. You can see another line back here. You can see more dunes back here. This is what a barrier island in its natural state looks like, except for right up here at the top where all the people walk up and tear up the vegetation to take their pictures. But this is what our dune system is looking like in its ideal state. This is what we've done to it in the West Galveston Island area. This is looking to the end of the Galveston seawall is pretty much right under where this picture is taken from. And you can see they're trying to come in and put a little dune here that's maybe 4 or 5 feet high, something like that. They're dumping out loads of sand and trying to protect this hotel here with a little bit of a dune. But huge difference from what we see down in Padre Island and in the National Seashore, because we've basically built all the way up to the edge of these dunes and on top of them. And these barrier islands are dynamic systems. They're not meant to be etched in place and anchored in stone. So when we start drawing property lines in somebody's house, the beach migrates back past somebody's house, they're saying, oh, well, I've still got a right to build a house there. But the fact of the matter is, you build a house on top of the dunes, you're tearing up the dunes, you're creating an erosion channel, all these things that are negative for the thing. And so had we known what we know now, we should have never allowed the level of development we did this close into the dunes. We should have allowed those dunes to stay there, stay in the state they were in, and it would have been much better for everybody. And when you get to the point where you've developed the area so much that the dunes are almost non-existent, this is what you get when you have a storm. This is subdivision on the Bolivar Peninsula right after Ike. The dune line at the time of the storm, you can see these black material. This is where the dunes were out here. There were several rows of houses back here, and they're gone. Nothing to protect them, no dunes, no nothing to break down the wave action, nothing to slow down the storm surge, just this one house, built by an engineer or something who supremely overdeveloped it or over designed it using concrete, and he's the only guy that survived, quite remarkably so, given the amount of debris that was washing around. But the reality is this is what it looks like when you don't have a functioning barrier island system, and this is what we're facing. So the proposal that's come out from the Corps of Engineers, and just to give you an idea on this, this was about a year and a half or 2 years ago, I think, that I put together this talk originally. At the time, it was a $23.5 billion estimate. I think they just got $32 billion approved by Congress for this, or at least by the House. So that cost estimate's gone up a little bit. If you know any history at all about Corps of Engineers projects, that won't be the final cost estimate. That won't be the final cost. But what they're looking at is kind of two components. They're looking at setting up a set of new dunes, a 12-foot and a 14-foot dune system, and I'll show you a picture of that later. Pretty much all the way down the Bolivar Peninsula past High Island, and then all the way down to San Luis Pass. This is meant to function as part of the coastal spine that's also being proposed, where they're talking about replenishing some dunes in other areas. But they're also going to put in a series of surge gates here at Galveston Bay, and then put a ring dike all the way around Galveston Island proper. And I'll show you a little bit about that, but it's going to start to look familiar. I call this ring dike the New Orleans Levee Starter Kit, because it's very similar to what they've done over in New Orleans, and I think it suffers a lot of the same pitfalls that ultimately, sunk New Orleans, if you will. So the idea behind this plan is to stop storm surge from the Houston Ship Channel and the sensitive infrastructure we've got up there. It's an admirable goal. I'm not sure this is the best way to do it. I'll show you what I think are some of the limitations, but again, I'm not making a value judgment. I'm just saying it's an awful lot of money for something that I don't think is going to ultimately be a long-term solution. So this is what their dune system is going to look like. You remember the dunes we showed down at North Padre Island? This doesn't really look like that. This is not a natural dune system. But what they're planning to do is have a 14-foot vegetated dune fronted by a 12-foot, what I call a sacrificial dune. It's just going to be a sand dune. They talked about armoring it to some degree, but that for aesthetic reasons, number one, that's less something people like. And it's also recognized in their design that it's going to be a dune that's going to have to be replenished. Every time we have a major storm that pushes any storm surge up in here, this dune is going to erode. It's going to wash out. And as a result, they've got, their design envisions, every 10 to 15 years or something, that they're going to have to come back here and completely rebuild this 12-foot dune. And so when you start talking about the amount of sand it takes to build a 12-foot dune from High Island to San Luis Pass, that's a lot of dredging, a lot of sand, a lot of material. We do have environmental concerns in the Galveston Bay system in our coastal waters, both from, older, petroleum releases out in the Gulf. Anybody who went to Galveston in the 70s can remember walking on the beach and getting tar balls on your feet. But we also have, dioxins, PCBs, heavy metals, things like that coming down from historic disposal pits and also from, industrial discharges that end up in our sediments. So where that sand comes from, what's in it, to me is a major concern. We're putting this onto a beach where people and kids are going to go and play and roll around and things like that. And then that material is going to get washed out from time to time. Where is it going to go? Is it going to wind up back here in an estuary? Is it going to wind up being pushed into San Luis Pass and plugging the pass? Where is that sand going? It's not just a matter of what does it cost to replace it, but what kind of damage is it going to do when it gets washed out? So those are the limitations I see in this design. I think it has its benefits. I think it certainly will be somewhat protective of the material, of the properties behind it. But in a really large storm surge, I don't know that it's going to function as well as they would hope. But that's, you know, I guess we'll see if they decide to build it this way. The other component is this ring wall around Galveston. I've included this ground elevation map. You know, if you think about New Orleans, most of the city is below sea level behind the levees. Behind this ring wall, and they're going to build floodgates across Offutt's Bayou here and some other channels that are down in this area that are going to, you know, supposedly be able to stop water from coming in here. And they're going to put a pumping station in so they can pump the water that does come in out. But you really, you know, think about that New Orleans map that I showed you with all those different levee breaks, all those different places where those levees were breached. What I see this ring wall doing is giving everybody, particularly down in this area, all these residential areas down here and everything down along here along the strand where they're, you know, 4 to 6 feet above sea level, it gives everybody there a false sense of security. Oh, they built a ring wall. I don't really have to have insurance for my house now, right? Because it's all protected. It's not going to flood next time. I don't have to have a plan for how I'm going to escape. I don't need to evacuate because it's not going to flood anymore. To me, it sets up a large risk profile that I don't, you know, there will invariably be small errors in the geology. There will invariably be small errors in the construction. There will invariably be things that are not accounted for in the design. And it only takes one to flood this area. You got a 25-foot storm surge coming in. It only takes one or two things going wrong, and you're going to have a whole lot of people who had a really false sense of security that they were protected, who now either have no insurance to rebuild their house or worse, may have stayed in their house in a situation where they should have evacuated. So, you know, we certainly can build the wall. It's within the realm of engineering capabilities. We're not protecting most of the infrastructure, the commercial infrastructure within this wall. So the water that's going to come in through San Luis Pass can still come in through San Luis Pass. You know, going back up to this map up here, you know, this is going to stop 14 feet of storm surge, right? So that storm surge isn't just going to go away. This is water that's moving to the north and west, presumably with the storm, and has winds ahead of it blowing from the east and northeast. So all of this storm surge that's accumulated along the coast that's not allowed to go across the dunes and across the island is going to go this way. And the first opportunity it's going to get is down here at San Luis Pass or down into the Freeport area. And if we don't include something down there, you know, we've got a lot of infrastructure down here in Chocolate Bayou, a lot of chemical plants. We've got the Strategic Petroleum Reserve at Bryan Mound. Got all these places that this water is basically going to be pushed to. All this sediment that's eroding, all this water is going to be pushed down here. And I think this is a setup for, okay, what do we have to do next time? This is the Mississippi River problem of, okay, we fixed this one. Okay, the next time all the helicopters will be down in Surfside telling everybody, oh, this is a terrible natural disaster and we're never going to allow this to happen again. So I think there's a lot of limitations to the design. I think we shouldn't see it as a one-time fix. It's going to require a lot of expensive maintenance, millions of cubic yards of sand to replenish those dunes when they erode. And, you know, frankly, it comes down to, is it worth the cost? If the price tag is 64 million instead of 32, and it requires, you know, or 64 billion, sorry, instead of 32 billion, and it requires, you know, $10 billion of repair and maintenance every decade, you know, is that worth it? You know, what are we protecting inside this wall here? Is that the responsibility of everybody to protect that, or is it the responsibility of the residents to buy insurance and be protected and evacuate when it's dangerous? You know, it's a design, or it's a decision that everybody has to make for themselves. I have my own opinions. You can probably guess what they are, but I think government is a word for the things that we do decide to do together. And so if we decide to do this together, I think we need to be cognizant of, you know, the impacts to the estuaries in Galveston Bay from the amount of sand that will be moving around, the impacts to the offshore environment, but also the impacts to the people who may think they're safe and aren't. You know, I think there's a lot of considerations that go into whether these projects deserve support or not. So I'll leave it at that. I'll just give you a quote from Mark Twain that he was talking about the Mississippi River and said 10,000 river commissions cannot tame that lawless stream, cannot say go here or go there and make it obey. And John McPhee, I think, followed this with, you know, I'm betting on the river. I kind of feel that way as well. You know, Mother Nature has ways to confound us that we've only started to think about, and she'll continue to do so. So we should be careful about how much we rely on our ability to control nature, and maybe try to find ways to work with nature and work with the geology and the geomorphology as we go along. With that, if anybody's got questions or anything, let me know. There's a few outside resources I've put up. I'll send a PDF of this to Kim, and
Yeah,
you
that'd be
guys can
great.
make it available so that everybody has access to these.
Yeah, that'd be great. And also your talk will be in the YouTube video that will be posted on the Heartwood channel.
Okay, great. So I'll leave
Appreciate
it.
it. It was fantastic. I'm a geologist, so I thought it was especially fantastic, but we got a
Thank you.
lot of good comments in the chat, especially about the case studies. We really like the case studies.
Everybody always does, so that's I was happy to be able to put a couple in here extra than above what I normally do.
Yeah. Just for the rest of everybody, we'll see you at the hike at noon at the Montgomery County Preserve Trailhead. And those of you that were logged on under a device like iPhone X or John's iPad or something like that, could you please in the chat tell us who you are? You've probably received a message. Just identify yourself so that we can give you credit for being on the chat live. And we just want to thank you again, Bill. That was fantastic.
Oh, no problem.
And everybody else, I'll stay on the chat for a few minutes. Otherwise, we'll see you at the hike.